Hi, I'm Professor Goings. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you come to the right spot, so go ahead and hit the subscribe button. That said, let's get into the current video. I'm going to discuss the product rule for radicals, and the product rule for radicals states the following. If I take the nth root of a product, a times b, what I can do is I can take the radical of each factor and then multiply. In other words, this is the nth root of a multiplied by the nth root of b. And of course I can read that the other direction as well, where if I multiply radicals, we can combine the radicands first and then take the root. So we'll do examples in both directions. Let me go ahead and illustrate how this works. Suppose I wanted to simplify the square root of 12. Now 12, of course, is not a perfect square, but we can factor it as follows. 12 factors as 4 times 3. Now I could continue going down through the factorization to get a prime factorization, but I see that 4 is a perfect square and 3 does not have any other factor, so that's as far as I'm going to take it. Now this would be the same thing then as writing the square root of 4 times 3. And again, if I look at my product rule up top here, if I have a perfect square, I can actually break this apart so that I have the square root of the first factor times the square root of the second factor. And like I said, since 4 is a perfect square, the square root of 4 is 2, meaning I can write this as 2 square root of 3. And so even though 12 is not a perfect square, I can find a perfect square factor and I can pull that outside of the radical. All right, let's do another example. Okay, let's look at the square root of 80. Right? 81 is a perfect square, but 80 is not. So let's take a look at the factorization, or a factorization of 80. And once again, I don't necessarily have to go all the way down to a prime factorization, but the goal is to find the largest factor of 80, which is a perfect square. Well, let's see how we could do this. Certainly I know that 80 is 8 times 10, so let's write that as 8 and then multiplied by 10. And I probably should have done that up here because I'm going to run out of room, so I'm just going to rewrite this up top. 80 factors as 8 and 10. Well, 8 I know is 4 and 2, and then 10 is 2 and 5. So it looks like I didn't break this down as efficiently as I could have from the beginning, but that's okay. If you don't see how to factor this to find the largest perfect square, just keep breaking it into primes and see what you get. Because notice I get 4 and 2 and 2, which is 16. So another way I could have broken down 80 is 16 and 5. And of course 16 is a perfect square. All right, therefore, if I go back to the square root of 80, this is the same thing as the square root of 16 times 5, and using the product rule, I will take the square root of the first factor and then multiply by the square root of the second factor. And of course, the square root of 16 is 4, so I get 4 root 5. Okay. And the product rule for radicals works for any radical. So in other words, any index that I want to take a look at. So let's take a look at a cube root. Let's do the cube root of, let's say, how about 24? Okay. Now, when I did this factorization in these previous examples, I was looking for the largest perfect square. Now I'm going to do a factorization where I look for the largest perfect cube. So 24, and let's break it down. And again, you might not see exactly how to break it down, especially to get the largest perfect cube, so we'll just keep breaking it into primes, especially if this is a significantly larger number. Well, let's see, I know 24 is 6 and 4. And I know that 6 is 2 and 3, and 4, of course, is 2 and 2. Well, notice that 24 then is going to be 2 times 2 times 2, so 2 cubed, which of course is 8. So 24, I would write this as 8 times 4. Now, sorry, 8 times 3. Now remember, if I was breaking this into a different factorization, like if I was doing the square root of 24, I would look for, say, 4 and 6s as far as I would go, because 4 is a perfect square, 6 has no perfect square factors, and I can't take anything from, 6 and combine it with the 4 to, again, get a perfect square. So therefore, this would be the cube root of 8 times 3, which would be the cube root of 8 multiplied by the cube root of 3, which is 2 cube root of 3. Okay. So this kind of illustrates one direction of the product rule for radicals, where I go from the left side to the right side, as you can see by going through these factor trees and finding whether if it's a square root, I'm looking for perfect squares. If it's a cube root, I'm looking for perfect cubes. Okay? Now, in the other direction, we can look at a completely different type of a question where I'm starting with something on the right-hand side and moving to something on the left-hand side. In other words, I'm going to multiply radicals together. So let me clean this up and then let me show you examples of that. Now, first and foremost, the sort of easiest case is if the radicals match. For example, if I wanted to do the square root of 3 times the square root of 7, since the radicals match, right, which is what I have in the product rule, then I just multiply the radicands together with that common radical. That means I would have the square root of 3 times 7, which would give me the square root of 21. Similarly, suppose I had the cube root of 2x, and I'm going to multiply by the cube root of, let's say, 5x squared. Okay, so suppose I was going to multiply those together. Well, again, the radicals are common. They're both cube roots, which means I would write this as 2x times 5x squared. But then I can combine terms here. 2 and 5, of course, would give me a 10. And then x and x squared will give me an x cubed. Notice then I can actually simplify this a little bit further, because this radicand has a perfect cube. And I can use the product rule again to write this as the cube root of 10 times the cube root of x cubed. And of course, the cube root of x cubed is equal to x. That means this becomes x times the cube root of 10. Okay. So in other words, if I'm multiplying two radicals together and the radicals match, then I just multiply the radicands. After I do that, I do want to do a secondary step, looking to see if that would break down any further. It did not here with the 21, because 21 does not have any perfect cube factors, whereas in the second example, I did have a perfect cube factor, which was the x cubed. Now, another type of question that you may see is, what if I multiply radicals and the indices of the radicals don't match? In other words, let's start with something like the square root of 2 times the cube root of 5. Okay. So how could I multiply those together? Well, what I'm going to do is I'm going to rewrite each of these radicals so that the radical turns into an exponent. I would write this as 2 to the 1/2. And then the cube root of 5, I would write this as 5 to the 1/3. Okay. Now, let's think about properties of exponents. Let me kind of put this off to the side here. If I multiply something to a power, let's say a to the m, and then b to the m, if the exponents match, then I can multiply the bases and bring that common exponent outside of that. On the other hand, if I multiply, let's say, a to the m and then a to the n, so this time the bases match, but the exponents may or may not match, then what I would do is I would add the exponents together. Okay, so let's see which one of those two is going to apply here. Because notice I have different bases and different exponents. Well, that would apply to this one on top here where I've got different bases and, well, actually it would apply to both because I've got different bases and different exponents. The one on top is different bases. The one on the bottom here is different exponents. Well, what I'm going to have to do is I'm going to rewrite this so that I can have some common exponents. 1/2 and 1/3. So let's find common denominators for that. Of course, the common denominator would be a 6. So this means this would be equal to 2. And then 1/2 would be the same thing as 3/6. And then 1/3 would be the same thing as 2/6. Okay. Now what I could do is, using, again, another property of exponents that says if I have a to the m to the n, that's the same thing as a to the mn. Now, remember that 3/6, for example, is the same thing as 3 multiplied by 1/6. So what I have is an exponent that's a product. I'm going to break it into two different exponents. So I'm going to take it to the cube, to the 3rd power, and then that to the 1/6 power. That means I'm going to write 2 to the 3/6 as 2 cubed to the 1/6 power. And then 5 to the 2/6, in a similar way, I'm going to write this as 5 squared to the 1/6 power. So after that manipulation, notice that the exponents now match. 1/6 something, 1/6 something, and that looks like the first statement up here where the bases could be different, but the exponents match. And of course, I could also write this as the 6th root, and 2 cubed, of course, is 8, and then multiplied by the 6th root of 5 squared, which is say 25, right? And then I now have product of radicals that have the same index. So that means I'm going to go from this side to this side, and I would get the 6th root of 8 multiplied by 200. And of course, I'm running out of room here, but this would be the same thing as the 6th, 25. Got ahead of myself, didn't I? 8 times 25. And of course, 4 times 25 is 100, so then double that, so I would get 200. That's right, preemptively wrote 200. And then I get the 6th root of 200. So this is how I would multiply different radicals. Thank you for watching, and please consider subscribing.